All right, we're back. Hopefully, the Brownson Lori stuff went okay for you. What we're going to do today is kind of a hodgepodge of stuff. I'm going to do my best to be clear, but not go for a million hours on this. We're going to look at the strength of acids and bases, what strong acids do, what weak acids do, why water's a real weirdo, and what's water's role and all this stuff, and just kind of put this all together. So there's going to be some things that you're going to have down in your notes. These are going to be some equations and stuff that you guys would be able to use down the road. So we're going to just get started with the strength of acids and bases. And we've already touched on strong acids and bases and who they are. We'll do a quick recap of who they are. But here's the whole idea, right? That stuff we did back in chapter 4 is totally different than this stuff because strong acids and bases react 100% in the direction of the strong things to the weak things, okay? So translation, what that means for us is that these guys are going to have a single arrow, no double arrows, no equilibrium. And that is the whole key to how this stuff is different than what we're going to look at today. Okay. So I'm going to flip this and show you guys the reactions or how strong acids look and strong bases look. And so you guys can see this right here. So the idea behind a strong acid and a strong base is this. If this guy's the acid and this guy is the base, what's going to happen is we're going to have this is our titration reaction that we did last year, and we would get some HOH or H2O, and we get some NaCl. We get in the habit of writing things as HOH because these guys are kind of separate entities, okay? This is a strong acid and how it would react with water. What we can do is we can have this react with water. Sometimes we don't have this react with water. They both will mean the same thing. You'll see what I mean in a little bit. It just kind of depends on what flavor your professor likes there. Okay, so I'm going to treat this like a Brownson-Lori reaction where we're going to get H3O plus and Cl minus. You'll notice a single arrow. Strong acids and bases will always do this where they react 100%. So if I grab a jar of HCl and water, I don't know why it's a jar, but it's a jar, and I looked in that jar, there would be 0 of this stuff and 100% of those guys swimming around. So that's the idea, okay? That's strong acids. Now, we need to relearn the strong acids and bases because finding the pH is going to be our goal. And when we find the pH of a strong, it's way different than finding the pH of a weak. So recap our strong acids. I'll probably forget some. It's hydrochloric, hydrobromic, hydroiodic, nitric, chloric, and we can put perchloric on there as well, okay? And then this one, which we'll get into down the road, H2SO4, the first H, and that will make more sense down the road, okay? So H2SO4 is a strong acid, the first H. The bases, strong bases here, would be things like anything that is a group 1 OH. So LiOH, NaOH, KOH, all right, all that stuff. Group 1 OH and a group 2 from calcium down. Okay, so calcium down. So calcium hydroxide, strontium hydroxide, barium hydroxide. Here's an example of how calcium hydroxide would be written, CaOH2. Okay, so those are the strongs. What we're going to look at today is how the weaks react and why equilibrium is established, and finding the pH is our ultimate goal. This is the thing that a lot of times professors are going to trip you up with, and finding the pH of a strong. I will tell you, when I was in college, when I was doing this stuff, it was one of those things that is a sneaky little professor move, finding the pH of a weak acid and how we go about do that. But that's a problem for future us. We're going to just continue on with this and try to, let's see here, talk about how weak ones behave. Okay, so weak ones. When two weak things react, equilibrium is going to be established. And the reaction that's favored is going to be the one where the stronger ones, and I have that in quotes because can you have a strong, weak acid? Yes. You guys will learn how this is down the road. We're going to use a fancy little chart that helps us out with this. But the stronger ones are going to the weaker ones. So that's going to be the reaction that's favored. Actually, we did this a little bit yesterday with the little chart that you guys had there, where there was the acid column and the base column, and you had stronger acids than other acids and stronger bases than other bases, okay? So here's the reaction here, okay? And we would have to use that chart on page 674, that one from the slides yesterday, to understand which reaction is favored out of these guys. So here we have HC2H3O2. That's called acetic acid. It's the stuff that's in vinegar. It's reacting with water, and it is establishing equilibrium, making H3O plus and the acetate anion. Okay, so when you look at the strength of this reaction and whatnot, and which one's favored, well, if this was chapter 15, we could figure out which one was favored if we knew the K. But we don't know the K for this yet, and we'll show you guys how to deal with that down the road. So what we can do is we can use that little chart on 674 and just kind of assign, here's the acid, here's the base, here's the conjugate acid, here's the conjugate base. And I could compare those two guys to each other and figure out which one is a stronger acid or which one is higher on that chart. And what I would find is that H3O is higher on the chart than HC2H3O2, which means that the stronger ones go to the weaker ones. So the reaction that is favored is the reverse reaction here. So in other words, at equilibrium, we're going to have more of this stuff than this stuff. And what you guys know about that is that this K is going to be less than 1. Okay, it's going to be less than 1 because that reaction is favored. Now, if there was more of this stuff than these guys, then the K would be really big. But you guys got to notice that most of the things for K in this chapter are going to be less than 1. Okay, so to understand how this stuff works, we have to understand how water works and this whole equilibrium with weak acids and weak bases. Water is kind of a very key component in the reaction here. So in order to understand this, and this is kind of like thrown in here, and I apologize for that. I'm trying to just get everything as compressed and succinct as I can. You need to understand what water does, okay? So water is amphoteric depending on the circumstances. Sometimes it can be a bracylaurie acid, sometimes it can be a bracylaurie base. Sometimes water reacts with itself. So if I have a jug of, distilled water or whatever, this water can react with itself in a couple of different ways. And I'll show you guys what those two ways are up here on the board. So I'm going to go ahead and just write these up for you so you can see how these reactions go. Some professors will write it like this, where you have H2O plus H2O making H3O plus and OH minus. So basically we take one of these guys and we say that's the bracylaurie acid, and this guy is the bracylaurie base, and the acid gives its proton to the base, so we have a conjugate acid and a conjugate base. Now, when you drink water, we're not worried about these guys reacting with us very much because there's not a lot of these reactions occurring. Here's another way in which this reaction is written, and then we will kind of show you how some professors will say, hey, instead of just reacting with each other, let's just break these guys up. Okay? So we have state of matter, liquid, liquid, liquid on this side, and all of these guys are going to be written as aqueous or dissolved in that liquid because they're at equilibrium. So erase that stuff. Here's the deal. What you guys hopefully remember about equilibrium is that solids and liquids don't matter in terms of our equilibrium constant. So with these reactions, if we wanted to calculate KQ. And by the way, these mean the same thing. Took me a while in college chemistry to figure that out because sometimes my boy Victor Day would throw up this reaction and then this reaction. I was like, what the heck, dude? Where did the H3O plus go? These things, for all intents and purposes, are going to be the same thing for us. Okay? So, what would be the K of this reaction? Well, the K of the top reaction would be products over reactants, but we don't care about the products over reactants. Or we don't care about the reactants because they're pure liquid. So we would write the KQ of the first reaction like that. Okay? The KQ of the second reaction, which, like I said, is going to mean literally the same thing for us, is going to be written like this. Okay? So, whichever one you want to go with, doesn't really matter. Sometimes the top one's more convenient, sometimes the bottom one's more convenient. I will tell you from my experience, the bottom one is what we deal with more. Now, because this is a special reaction that occurs in water, and we said it doesn't occur very often, this is a special K that we call K dub. Okay, so water, and I believe this is at 25 degrees Celsius. Remember, the value for K will vary based on temperature. Temperature is the only thing that messes with K. So at 25 degrees Celsius, water does this, and this is the value of K. We call this K dub. Okay, I'm just going to do the lazy person's version of this. So this right here, boom. Know that it's called K dub. Know that that is an equation that you'll have to use. It's 1.0 times 10 to the negative 14th. That is going to be your friend. That is something that if you are a person that stores numbers into your calculator, you would store that as W. All right? So there's that. We'll just forget that. All right. Now, the reason that we pay attention to the H pluses and the OH minuses and all that stuff, we'll just fly through that, is because this will tell you if a solution is an acid, a base, or neutral. You might notice that H plus and OH minus are kind of like the codes that we used to use for acids and bases. I see H pluses, I think acids. I see OH minuses, I think bases. So the idea behind this is a solution that's aqueous is going to fall into one of these three categories: neutral, acidic, or basic. And the idea that follows with that is right here. It is neutral if the H pluses are equal to the OH minuses, like in pure water. Pure water is going to have the same number of H pluses swimming around as OH minuses. We can find that from KW, and actually the value would be, because we know KW is 1 times 10 to the negative 14th, and that's equal to the H plus times the OH minus, right? So if that's X, and there's two X's, these things are exactly the same in pure water, we divide that. That means that in pure water, the H pluses and the OHs are both equal to that number, okay, in terms of molarity. So that's why we don't get fried, or esophagus doesn't fry when we take a drink of something that is pure water, okay? Not that a lot of things are pure water that fry our esophagus, but whatever, right? So neutral, H plus is equal to OH minus. Acidic, H plus is greater than OH minus. Basic, H plus is less than OH minus. Okay? So all aqueous solutions will fall into one of these three categories. Obviously, to get to this category, there's got to be just the right number of things. We throw anything that can break into H pluses, it makes it acidic and basic. And these values will always fluctuate with each other. So that's going to be kind of our goal in when we get to the point of calculating pH and the pH scale. So the pH scale. The pH scale is a logarithmic scale that we use to measure H plus concentration. So pH is equal to the negative log of the H plus. Now I know when you see logarithms, you probably do a little vomit in your mouth because logarithms are kind of scary in your math classes. But for us, it's just a button on your calculator. So we would pick the negative log of the H plus concentration. So if we had a concentration of 0.01 for H plus, we would just take the negative log of 0.01. Low pHs equal lots of H pluses. What you'll notice about this logarithmic scale is that the lower you go, the more on the pH scale, the more acidic it is. Okay, so the bigger that number gets in terms of H plus, the lower the pH gets. If we're below 7, we're acidic. Okay, and because it is a logarithmic scale, the pH value, each pH value of 1 is actually a factor of 10. So like if you're comparing the pH of, something that has a pH of 3 with a pH of 1, you think, oh, 3 to 1, that's not a big deal. It's just 2 units. It's actually 10 times 10 or 100 units more acidic, the thing that has a pH of 1. So that's our pH scale. The pH scale goes from traditionally 0 to 14, but it can be negative. It can go above 14. You'll see down the road. Something that I'm not even sure if we did this last year or not. We might have touched upon this when we were doing titrations, is the pOH scale. The pOH scale is a scale that's more convenient to use when you have OH minus concentration. So let's say I don't know what the H plus concentration is, but I do know what the OH minus concentration is. I would use the pOH scale. It's the easiest one to use there. So it's the same idea. On the pOH scale, the lower you are on the pOH scale, the more OH minus you have. So the pOH scale traditionally is from 0 to 14, and 7 being right in the middle. And if you are lower than 7, you have more OHs, you're more of a base. Now, the little cheat code between these two scales is that in an aqueous solution, the pH plus the pOH will always equal 14. So the way that we measure pH, once again, this is hard to do without the lab setting, is we use a pH meter, or we use these things called indicators. You have these test strips. If you dip them in a pool or a hot tub or anything like that, or a fish tank, and they change colors, one of the things that will change is the pH. And there's different types of indicators. Last year, we used phenolphthalein for our titration. It was clear. And then it all of a sudden turned light pink if you were a boss at titrations, and dark pink if you were not a boss or you dumped too much stuff in. Okay? So those are some scales that we will use and put that together with KW. So the whole idea here, and this is something I missed in college a little bit when I first started learning this, is that if you are an aqueous solution, even if you're an acid, you have H plus and OH ions in you. That's just kind of the key to aqueous solutions. You got to have both of these things in you if you are an aqueous solution. So acids will have more OH plus and bases will have more OH minus. Okay. So question is how do we use KW to figure this out? Find the H plus concentration if a solution contains 0.150 molar OH minus. So let's see how we would tackle this. All right. So if we're going to use KW, we know that KW is always going to be equal to this value. It doesn't change for us, okay? It's not going to change for us. We're going to try to keep it simple. I'm going to mess with the temperature and change the K. So that value is always equal to the H plus times the OH minus. So if you know one, you know the other, assuming you can do division. So if I want to know the H plus and I only know the OH minus, how do I solve for that? Well, there's X. You do division. We would take 1 times 10 to the negative 14th divided by 0.15, and we would get the H plus concentration is 6.67 times 10 to the negative 14th, and this is molar. Okay, so here we have a solution where its H plus is 6.67 times 10 to the negative 14th, and the OH minus concentration is 0.150. Okay? Is this an acid or a base? Here's how you could do that. You look at which one's bigger. This number is much bigger than that number, therefore this is a base. Okay? If you don't trust me on that, you could find the pH and the pOH. You could take the negative log of this number to get the pH. You could take the negative log of that number to get the pOH. You could look at the acid-base scale, and you could figure out if it's an acid or a base. Okay? This kind of puts all this stuff together. I apologize for this being just kind of out there, and there's a lot of stuff that goes into this. Okay? All right. So why don't you guys try this one, and I'm going to pause you here. Oh, look at that. It's 10:29, right? Perfect timing for 4th hour. So I'm going to pause you guys on that. Find the concentration of OH minus in a solution that contains 0.565 molar H plus. Boom. There's the answer. We took KW divided by 0.65, and we ended up with that. Okay? So that is how we would do that. Okay. All right. So we'll move on to finding pH of strong acids and how this works. We'll do weak acids later. Everything from here on is going to be a strong acid or a strong base. Okay, so quick reminder, strong acids and bases ionize 100%. That makes finding the pH much easier just because whatever the concentrations of your initial solution is, that's going to be pretty much the concentration of your H plus. We'll use a little stoichiometry to figure out this, and I'll show you guys how to do this. So our goal is to find the pH of 0.245 molar HCl. Now here's what you will eventually have to get to. The point of identifying that this actually is a strong acid and makes it a little bit easier. Okay, so let me show you the reaction, and we can. Okay, so I'm just going to write this. I'm not going to write it with water. I will write it with water. I'm going to show you guys how, because I just don't want you to have a professor that writes it differently and have you guys go, what is happening? Why is he doing that? Okay. Because he hates you or she hates you. That's why they're doing that. All right. So both of these reactions are exactly the same. They're exactly the same. HCl breaking H plus and Cl minus. HCl while reacting with water to make H3O plus and Cl minus. So like I said, that is that. So in order to figure out what the pH is the negative log of the H plus. So what we would have to do is we'd have to figure out what the H plus is. Here's the nice thing. I want you guys to notice that all of these things are 1-to-1 ratios. That's 1, that's 1, that's 1. Okay? So because those are, I'm going to erase this one because like I said, it's going to be the same thing. Because this is a 1-to-1 ratio in terms of moles, then that means our concentrations of these things are exactly the same. If that's 1 mole, that's 1 mole, that's 1 mole, and we're all in the same container, and that would be 0.245 moles per liter. That's 0.245 moles per liter. That's 0.245 moles per liter. So to find the pH, we're going to take the negative log of 0.245, the solution. Now, use your freaking brains here. HCl is an acid. So our pH should be less than 7 if we do this right. Sometimes we forget to check that, okay? So let me give you guys a second to type that in your calculator here and see what you guys come up with. So, sorry for the pausing and stuff. I had to grab a calculator that actually knew where the log button was. So we would take the negative log of that, and I would get a pH of 0.61. And what's the label? We don't label it, all right? We don't label it. For right now, I'm not going to worry about sig figs with pHs and such just because there's this weird rule, and it's just going to be easier just to we get plus or minus a sig fig in here anyway, so we'll go from there. All right. So That's the idea behind finding the pH of Strongs. We can find the pH of Strongs and weaks. Here's a couple of examples that we will do real quick here. Let's just go ahead and I'll just put them on here. All right, so putting this all together, right? What is the pH of 0.15 molar KOH, right? So this is the dirty trick that professors will do to you. pH, KOH, those two things don't jive, okay? So the easier thing to do when you have a base like this, an Arrhenius base, is to find the POH, then find the pH. So once again, this is kind of a what you see is what you get here. This is a 1-to-1 ratio. So if this is 0.15, then that's 0.15, and that's 0.15. So the POH would be the negative log of 0.15. Negative log 0.15. Okay, so we would get 0.82 for the POH. That doesn't answer our question, what's the pH? So the pH, on an earlier slide, this is kind of the nice little pH Da Vinci code here, is that those values will always equal 14. So to find the pH, we take 14 minus 0.82, and we would get about 13.2 is the pH. Now, time to use your freaking brain. Okay, what do I mean by that? Well, that's a base, and a base has to have a pH greater than 7. If you put that as your answer, then you didn't use your freaking brain, because that's less than 7. Okay, POHs for bases are less than 7, but not the pH. pH is going to be greater than 7. So that's how you would tackle that. Okay. Last one here, find the pH of a 0.656 molar CaOH2 solution. So here's what I want you guys to notice. This is a little bit different than the previous one because of this move right here. What's different about this guy is that instead of just one OH, you get 2. So this is not a what you see is what you get. That's a 1-to-1, but you get twice as many OHs as you do from that. So 1 mole of this stuff will give you 2 moles of that stuff. So the actual concentration of the OHs swimming around there is 1.31. So if we're going to find the pH of this solution, we are going to take the negative log of that number, but that ain't going to give us the pH. That'll actually give us the POH. Once again, this is a base. So sometimes it's more convenient to find the POH first, then answer the question about pH. Okay. So how do we do this? First thing we do is we find the POH. And this is where it's going to get a little dodgy here, and I'll show you how in a second. Okay, so the negative log of 1.31 is a negative 0.12. That's the POH. Is it legal to have a negative POH? Yes. Is it legal to have a negative pH? Yes. So that's the first step. Now, if we know that pH and POH is equal to 14, okay, so if this guy is negative 0.12, we're going to actually add that. So the pH of this solution is about 14.12. Here's the pro tip. If you are off of the scale on one end of the spectrum, traditionally the pH and POH scales are from 0 to 14. If you're off the scale on one side, say for example, our POH is negative, then that means that our pH will be off the scale on the other side. You'll be greater than that 14. Okay? So that's kind of the idea behind that. Right? Last thing I'm going to say, I've talked way too long. but you need to be able to do this. And I don't want to get too mathlete for you here. And that is working backwards, finding the H plus and the OH minus concentration if you actually know the pH. Okay. So here we have an HBr solution. HBr is going to break into H plus and Br minus. Okay. Now, you'll notice everything here is a 1-to-1, but here's the deal. Our goal is to find the H plus, and then we can find the OH minus. I'll show you guys two different ways in which you can do this. So when you have the pH, but you want to go back to H plus, you need to get this equation in your life. To find the H plus from the pH, you take 10 to the negative pH. To find the OH minus from a POH, you take 10 to the negative POH. Now, this just works with that whole logarithmic thing. Like I said, I don't want to talk too much about the algebra behind it, but that's how you eliminate it. If you're looking for that button, don't look too far, because literally your log button second function is usually a 10 to the X, okay? So if I want to know the H plus, what I'm going to do is I'm going to take 10 to the negative 1.34. That'll give me my H plus, and I go ahead and calculate that, figure out what that mess is. So 10 to the negative 1.34 is going to be, I'll put it right here. You see that? All right, 0.0457 molar H plus. If I want to find the OH concentration, I have two ways in which I can do that. I can plug that into Kw and use the Kw that we did earlier, or I can find the pOH of this solution. So 14 minus 1.34 is 12.66, and I just take 10 to the 12.66. So 10 to the negative 12.66 is going to give us 2.19 times 10 to the negative 13 molar. So usually with these acids and bases, here's what you find. One number's way bigger than the other. Okay, so that's all I got from that. That was fast and furious, and I hope that if you have questions, just send me an email or whatnot. Be checking Classroom and for our assignment on this stuff.